We're going to finish up Chapter 8 by looking at two sample proportions. The two samples are random, they're independent, where the number of successes and failures is at least 5 for each of the two samples to be used in the hypothesis testing about a claim about the two population proportions. So, we're going to use our two samples, P1 hat and P2 hat, to make a claim about the populations P1 and P2. We have to have a pooled sample proportion in this case, which is x1 plus x2 over n1 plus n2. So note they are coming from our two proportions. That is P bar. Q bar equals 1 minus P bar. Again, P and Q always have to add up to be 1. They are complements. Here is our test statistic. P1 hat minus P2 hat, subtract P1 minus P2, all over P bar Q bar over N1 and P bar Q bar over N2, and then square rooted. Please make sure that when you're doing this, you do not forget the square root. We need to use table 4. We're going to find a z-score, and we can either do the p-value, which would be comparing the area of the p-value to the area alpha, or we can do the critical value using alpha, which will compare the test statistic with the critical z-score. If we want to do a confidence interval, again, this is very similar to what we had before. P hat 1 minus P hat 2, subtract the margin of error, and then on the other side add the margin of error. And again, if you look back to an earlier section in which we were doing the hypothesis testing for one sample using proportion, you would find that all of this would look very similar. It's just that we've expanded it a little bit to include both samples. So, what we're going to look at is the situation in which we have front seat occupants involved in car crashes, and we're going to look at whether airbags made a difference or not. Use a 0.05 significance level to test the claim that the fatality rate of occupants is lower for those in cars equipped with airbags than those that didn't have airbags. And so we have here a total of 11,541 occupants, of which there were 41 fatalities, and here 9853, of which there were 52 fatalities. And again, part of the idea here is we know that the numbers are different, okay, and our proportions will be different because the denominators are different. So we know all that. The real question is, are they different enough that we can make a claim that the airbags made a difference? Or could the differences between these two samples simply been a matter of random chance? That's really what you're trying to do with hypothesis testing. Alright, so we're going to start off with the p-value method. First, are the minimum requirements met? We do have two random samples using proportions, and all the data values are greater than 5. Okay, our claim, P1 is less than P2, that the airbags made a difference, so P1 is less than P2. Counterclaim, again, null hypothesis always gets the equal sign, and our alternative hypothesis is back to our claim that P1 is less than P2. Alpha is 0.05. Find our pooled values, P bar, 0.004347, and then Q bar will be 1 minus P bar, and so we get 0.995653. In this case, I am carrying a lot of decimal places to make sure that I don't have any rounding errors in it. For example, if I only went to 2 decimal places, this one would be 0, and in the following equation, basically we would have a lot of zeros. We'd be dividing by 0. We couldn't get a result. So, a lot of decimal places to help in this case. Again, we're using normal distribution table 4. We find our test statistic, P1 hat minus P2 hat. So here's P1 hat minus P2 hat. P1 minus P2 is 0. Again, the null hypothesis is there's no difference between the two proportions, and therefore If you subtract them, it's 0. And then our p bar, q bar over n1, p bar, q bar over n2, and we get a z-score of negative 1.911. It's a left-tail test, and so when we look up negative 1.91 in table 4, we'll get an area in the table of 0.0281. So that is our p-value. Now our comparison step, since the p-value of 0.02 is less than alpha of 0.05, which means the area is smaller, it's more extreme, we reject the null hypothesis. And again, the null hypothesis is that they're equal, so we're rejecting that these are the same proportions. And therefore there is sufficient evidence to support the claim that airbags reduce fatalities. And so that is the p-value method. Now we're going to go to the traditional method or critical value method next. And again, the only difference between the two methods is the p-value compares the area of the p-value to the area of alpha, and then the critical value or traditional method compares the z-scores that bound those two areas. Now, all of the beginning steps would be the same. So, we still have to have our claim, counterclaim, hypothesis, alpha. We still have to find the p-bar and q-bar. Okay, we're still going to have to find the 1.911, negative 1.911. We still have to do all of that. What's different is we're not going to do what we had at the very bottom. Instead, in this case, we're going to take our alpha and go find the z-score that would go with that alpha. And it turns out the critical value would be negative 1.645. It's a left-tail test. Again, it's a left-tail test because our claim is less than. Now our comparison, since the negative 1.911 is less than the z-score, the critical value z-score of negative 1.645, meaning it's in the rejection zone, we reject the null hypothesis, and we say there is sufficient evidence to support the claim that airbags reduce fatality. These should match up because one just has the area, the other one has the z-score that would bound that area. And again, all the beginning steps would be the same. Confidence interval, again, all our beginning steps are the same, and we still have to find the critical z-score so that we can put it into the margin of error equation. Note that these are P1 hat and Q1 hat, P2 hat and Q2 hat, not P bar and Q bar. So we go ahead and put all those in, and again also note that a 41 out of the 11,541 is P1 hat, then the rest, 11,500 out of the 11,541 has to be the Q1 hat. We end up with a margin of error of 0.001507. Now our actual confidence interval equation looks like this. To help in our calculations, let's just go ahead and find P1 hat minus P2 hat. So the 41 over 11,541, subtract the 52 over the 9,853, we get negative 0.01725. So negative 0.01725, subtract negative, or subtract the 0.01507 from up here. And then on the other side, negative 0.01725 plus the 0.001507. And so we end up with negative 0.003232 up to negative 0.00218. Now, note that the confidence interval does not contain 0. The entire interval is less than 0. They're all negative values. Therefore, this can't be true. Since if P1 did equal P2, we would have a 0. So the fact that the entire interval is less than 0 means that P1 doesn't equal P2, and we have to reject the null hypothesis that says they do equal each other. Therefore, there is sufficient evidence to support the claim that airbags reduce fatalities. The null hypothesis is always assumed to mean no difference or no effect. Since we rejected that, we're saying there is evidence to support a difference or an effect. P1 equals P2 would mean the airbags had no effect on the number of fatalities. Please note, we did not prove using airbags saved lives. We just concluded there was sufficient evidence to reject the null hypothesis that airbags made no difference. And so that concludes Chapter 8.